In this video, we're going to tackle the task of trying to determine which of the various reactants is the limiting reactant using the information that we're provided. So our learning goal is going to develop basically a systematic method for determining which is the limiting reactant. We're going to use mole ratios as our indicators for this. The moles are basically the amount of each species that are present in the reaction. So even if we're given amounts in grams, we should convert them always to moles because that's what we can directly compare using the balanced chemical equation. What we're going to do then is compare the actual mole ratio that we get from the amounts that were given in a reaction to the theoretical mole ratio, which is indicated by the balanced chemical equation. So the numbers in front of the species in the balanced chemical equation basically tells you ideally how much stuff should be there, but the actual case, in fact, might be different. So let's go back to our earlier example, this reaction between sodium hydroxide and aluminum oxide, and we're going to look at some examples that involve this particular reaction. So our actual ratio, and this is from the example we worked in the last video, was that we had 0.467 moles of aluminum oxide, we had 1.19 moles of sodium hydroxide. So what we want to do is use that information in a more systematic way than just using them both to calculate how much of the product, the aluminum sodium dioxide, is produced in this. So what we can do is basically divide these two. If I divide those two numbers, 0.467 divided by 1.19, I would get a ratio of 0.392. Now, what good does that do me? Why am I worried about that particular ratio? Well, I know what ideally the ratio should be from the balanced chemical equation. If I look at the coefficients in front of those species in the equation, I see a 1 in front of the aluminum oxide and a 2 in front of the sodium hydroxide. So I know that theoretically there should be a 1 to 2 mole ratio of these two. So when I divide these two, I get a different number. I get 0.5. So now the key is to compare these two numbers. Okay, it's pretty easy to tell. 0.392 is less than 0.5. Now what does that mean? What is that telling me? Well, this ratio that I've taken is the aluminum oxide to the sodium hydroxide. And the actual amount I have is less than the amount that would be indicated in the ideal case. So there's two ways I can look at that. I either don't have enough stuff in the numerator or I've got too much stuff in the denominator. But both of those point to the same result. If I don't have enough stuff in the numerator, it means I don't have enough aluminum oxide. So in effect, what this comparison of these two ratios tells me is that there is less aluminum oxide than I need in order to react with that total amount of sodium hydroxide. So the aluminum oxide must be the limiting reactant. Okay, we're going to do a little practice activity here. And again, I'm going to ask you to pause the video and try to work this out. This is a little bit more difficult case because you're given grams of each of these reactants and you're going to need to figure out which of them is the limiting reactant. Okay, pause the video and try this out, and when you're done, come back and I'll give you the answer. All right, hopefully you got to a good answer. I hope you converted to moles first because that's what you need to do. When we convert to moles, we find that in the case of aluminum oxide, we have 8.93 grams. We divide by the formula weight of aluminum oxide, we have 0.0876 moles. When we do the same for sodium hydroxide, we had 6.07 grams. It's got a formula weight of 40, so that gives us 0.152 moles. So now what I want to do is I want to take these actual amounts of moles and divide them and compare their actual ratio to their theoretical or ideal ratio. So in this case, the ratio is 0.0876 divided by 0.152. So my actual ratio is 0.576. But the ideal ratio, this is the same ideal ratio as we saw earlier in this video, is 0.5. So now my actual ratio is greater than my ideal ratio. So again, analyzing the fraction that I've used to get this, it tells me that what I have in the numerator is too large. So I've got more aluminum oxide than I need to get this reaction to go. I don't have enough sodium hydroxide. So that's a sure sign that sodium hydroxide is my limiting reactant in this case. All right, so now that I know the limiting reactant, let's figure out how much stuff we can actually make using that limiting reactant. So when we take our limiting reactant, whatever much we have, and we determine how much product can ideally be formed, this is something we call the theoretical yield. One reason we need to use the limiting reactant, because if we use the one that was in excess, then we would predict a theoretical yield that's greater than we could actually produce from that reaction. So we always want to use the limiting reactant to do this. So if we were to calculate the total number of grams of aluminum sodium dioxide that are possible from this calculation, this is basically a moles to grams stoichiometry conversion, and we would have an equation that would look something like this. If this is seeming foreign to you, go back and look at the earlier video and reacquaint yourself with these stoichiometry problems. We started with 0.152 moles of sodium hydroxide. The mole ratio of these two is 2 to 2. That's the coefficient in front of each of them in the balanced chemical equation. And the formula weight of our product is 81.97. So when I get through doing all this multiplication, I should end up with 12.46 grams of our product. That is our theoretical yield. It's what we calculate we should be able to get if everything runs perfectly and we use up all of our limiting reactant. Now let's suppose that I'm actually doing this experiment in the lab, and I run this very experiment with the same amount of starting materials, and what I get is an experimental result that says 9.748 grams is produced. Now, does that mean my theoretical result was wrong? Did I make a mistake in the math? Well, no, this is the actual yield, and one of the things that we have to face as scientists is that our experiments don't always get carried out perfectly, and in fact, error in the experiment and things that get wasted along the way can cause us to get less than our total amount out of our experiment, to less than the yield that we expected for the theoretical yield. One thing I will say is the actual yield is always an experimental result. The theoretical yield is always the result of a calculation. The actual yield must always be less than the theoretical yield. If you get more actual yield than you got theoretical yield, then you've got even bigger problems. Your actual yield should be less than the theoretical yield. But this leads us now to evaluate what is the percent yield. The percent yield is basically a comparison of these two yields with one another, and we're going to define it in a very particular way. The percent yield is basically the ratio of the actual yield to the theoretical yield times 100%. Now, remember I said the actual yield is always less than the theoretical yield, so this is always going to be a fraction less than 1. So the percentage that I should get should be some percentage between 0 and 100. So from our previous example, what we should get is the following. We got an actual yield of 9.748. We calculated a theoretical yield of 12.46. So that would leave us with a percent yield of 78.23%. So pay attention to this definition. It's something that you'll need to know for doing problems in the course. It's probably also something you're going to run across in your own work of one form or another as you go along.